Hello everyone. Welcome to problem 2.4 of David Griffiths Electrodynamics. Alright, so let's get started. The problem statement says that we have to find the electric field, a distance z, above the center of a square loop of side lengths a that carry a uniform line charge of lambda. And it gives us a hint to use the result of example 2.2. All right, so I try to draw a decent figure here of our setup. So we have a perfectly square wire here, 4 edges. Each edge, the whole square wire carries a uniform charge of lambda, and each side length is a, which gives us the half distance here across is a over 2. And I've denoted the height here to above the center of the loop z at some point in space. And I try to draw a line from the point that we're trying to find the field at and a point on the edge of the wire here with the distance of script r, and gave that an angle of theta between this line and this line. So we're going to have to solve example 2.2 from the book, and we don't necessarily have to solve it, but I want to solve it for you guys. It does show the answer in the book, and I just want to kind of explain some of the logic here of why example 2.2 is similar to this problem and how we can use that answer. So if you picture moving this charge here and moving it across to be above this side of the wire here, so that's not above the midpoint but above the side of the wire, well then what you essentially have is this problem, where the point that we're trying to find the field at is directly above one of these side lengths along the square. And if we can figure out what the electric field is due to this configuration, then it's merely a problem of essentially substitution of a change of variables when we move the point away from being directly above the wire and kind of pushing it back out towards the center. It's merely just a substitution or a change of variables at that point. And there's nothing special about any of these sides of the square loop. They're all equally the same mathematically. And so if we could find the electric field due to one of these sides, then mathematically, the total electric field would just be equal to 4 times that, because we have 4 sides here, and each side would contribute exactly the same amount. You could rotate the square any different way, and it doesn't matter what side you're using. So we're going to think about it like that. So first, let's think about this example problem where we have our point in space that is directly above this uniform line of charge, and the example, they give it a length of 2L. So we're gonna work with this for now. So what is the electric field due to this line of charge in length 2L at this point in space? Well, it produces a field out this way. If you think about a small unit of charge here on the wire, a small differential amount of charge dq, it would produce a field out this way, right? You can say dE1. However, this is a very symmetrical situation. If it's at the midpoint, you can find an equal charge that's the same distance away from our origin here on the other side, like let's say over here, that produces an electric field out this way, where the components of these two fields, well, this one has an x component. If I label this the x-axis and this the z-axis, well, the component is this way for the x component. have the z component this way, and then this electric field has an x component this way, and z component this way, and the x components cancel out, and all we get are the two vertical components contributing to the electric field here. So really what I'm saying is the total field is actually just a field of the vertical or the z components. All of the x components of every little charge on this wire end up canceling each other out. And so given that we define this to be angle theta, you can define this to be the angle theta, and we get that DEZ would just be DE times the cosine of theta, where the cosine of theta is z over script r, and where script r is the square root of z squared plus x squared. So, a lot of these problems are starting to get very repetitive with all these different terms here. Very similar, a lot of these problems are. And what is the magnitude of the of the small differential field produced by one of these infinitesimal charges? Well, given that you can think of these infinitesimal charges as point charges, then it's going to be 1 over 4 pi epsilon naught dq over script r squared, or 1 over 4 pi epsilon naught lambda dx over z squared plus x squared. And then just plugging that into here and plugging in cosine of theta, what we find, plugging everything in, dEz, the z component of the field, or the differential amount at least, is 1 over 4 pi epsilon naught. We have lambda dx, and then we have z squared plus x squared on the bottom. However, with cosine of theta, we're going to have a z on top. Let me put the z here. Over script r, which is the square root of z squared plus x squared. So we end up having z squared plus x squared to the 3/2. I'll just let you guys do the algebra there. Cool. And we could put a vector on this if we wanted to. So that is the vertical component, or the z component, of the electric field due to any infinitesimal charge along this wire. And so how do we find the total field? Well, we just integrate over the whole wire. All right? So let's go ahead and do that. All right. So the total vertical component of the field is going to be the integral from x equal to minus L to L, because our origin is 0 and all the way to the left is L. If the whole length is 2L, oops, there we go. If the whole length is 2L, then the half of the length is L, right? So, all right, let's, so this would just be DEZ. And so plugging all this in, I'm going to factor stuff out actually. So we're going to have lambda times z over 4 pi epsilon naught, the integral from minus L to L of 1 over z squared plus x squared to the 3/2 power dx. And this is an integral that we did in the last problem, actually. I'm pretty sure this exact integral here. So we can solve this by using trig substitution. So we let x be z tangent of theta, and that will give us the answer we want. So that means dx with respect to theta is z secant squared of theta, since the derivative of tangent of theta with respect to theta is secant squared. And then plugging all that in, we get that EZ is, let's see, we have lambda z over 4 pi epsilon naught, the integral from minus L to L. So dx, so we're going to have z secant squared, so I'm going to factor out that z and pull it out, so it's going to be z squared there. And we're going to have secant squared, oh, I forgot my d theta here. So secant squared of theta d theta. And on the bottom we're going to have, well, x is z tangent of theta, so x squared is z squared tangent of theta squared. So we'll have z squared plus z squared tangent of theta squared. So we can factor out a z squared. And then we have 1 plus tangent squared here. But this is all still raised to the 3/2 power. I haven't taken that out. And then applying the power to each of these terms here, oops, with a closed parenthesis, we have that EZ, so we have lambda z squared over 4 pi epsilon naught. So z squared to the 3/2 is z cubed. So we have z cubed on the bottom here. I can pull that out and that'll cancel that. Then we have our integral still, minus L to L over secant squared of d theta. And 1 plus tangent squared using the trigonometric identity is secant squared. So this will just be secant squared raised to the 3/2, which will just be secant cubed. So what we end up having is secant squared of theta d theta over secant cubed of theta, which is just, cancel that, and that will be 1 over secant of theta, where secant of theta is 1 over cosine, so we have 1 over cosine, which is just cosine. So what we end up having is lambda over 4 pi epsilon naught z, the integral from minus L to L, and these bounds are still in x. I did not change them over to theta. We have the integral of cosine of theta now, d theta. That's a very simple integral. That's sine of theta. So we have EZ is lambda over 4 pi epsilon naught z, sine of theta from minus L, evaluated between L and minus L. However, what is sine of theta? Sine of theta, from our picture, is x over script r. Okay, and where script r is the square root of x squared plus z squared. So we plug that back in so that we can evaluate our bounds in terms of x. So we find that the z component of the field, or at least the magnitude of it, is lambda over 4 pi epsilon naught z times x over the square root of x squared plus z squared, still evaluated from minus L to L. Now we can actually evaluate it, so I'm going to pull out the common term here. So these are all constants, 4 pi epsilon naught z. And then once we evaluate our bounds, we'll have L over the square root of L squared plus z squared. And we have a minus, but we also have we're evaluating at minus L, so we have a minus L over this, so it's going to actually be a plus, and it'll end up being the exact same term. Minus L squared is positive L squared. And so these are the same terms, so it's just twice of this. So we find for our fields, lambda over 4 pi epsilon naught 2L over the square root, I forgot my z here, L squared plus z squared. And yeah, that is the field for example 2.2. This is not the field for our real problem. Remember, this is for example 2.2, which we're going to use this answer to find our field that we're looking for. All right, so just to summarize real quick, this answer is the electric field due to this uniformly charged wire of length 2L at a distance z above the midpoint of the wire. And again, why did we solve this problem if our real problem is this? Well, what we solved essentially is, if we moved our midpoint, if we moved our point that we're trying to evaluate the field at from the middle of this square and moved it over to above the midpoint of this wire, then that's exactly what we've solved here. So now let's try to take our answer here and turn it in terms of the variables here if we did happen to move our point over back to the midpoint of the square. So what I'm saying is, so for this case, so L here, the length of this whole wire was 2L, correct? And so in our problem, the length of the wire is A. And that means half of the length of the wire is A over 2, and half of the length of the wire here was L. So what I'm saying is, for our problem, if we want to change this answer to fit our problem, the L in this problem is going to be A over 2 for our problem, right? Because half of the length of the wire and here on this problem was L. However, for our problem, half the length is A over 2. Okay? That's the first thing we have to do. And then, in this problem, the distance from the distance above the wire here, between the wire and the point we're evaluating the field at, is z. In this problem, if you thought about it, if you thought, hey, first the point was over here, right? Like if you think about it where the point was over here first, right? Let's say the point was here, which is essentially what our problem is down here. Then yeah, that distance z here, this vertical distance, is the same as this distance here. But if you shift that point over to be here, this distance z becomes this distance r. So in the example problem, z is now going to be our script r. So z in our answer here, we're actually going to translate that to our script r, which is the square root of z squared plus a over 2 squared. Which is like yeah. I'm just trying to show you. So script r for here, script r is equal to, or is the square root of z squared plus a over 2 squared. So these are the sort of transformations we have to make. And this z in the square root, I should really call it like z prime. It's a different z. Well, in a way it's not a different z, but it's a different, we should really call it a different variable. So this z is the z from the example problem, when it was straight above the wire. And this Z is the distance here above the midpoint of the square. So using these variable transformations, we can say that the electric field, I'm going to get a new piece of paper. Let's see. We can say that the electric field, due to just one side of that square, the magnitude of it is going to be, let's plug everything in. So we have lambda over 4 pi epsilon naught. And we have z on the bottom. So that's going to turn into L squared, or sorry, Z squared. It's going to turn into Z squared plus A over 2 squared. And then we have, let's see, times 2L, so times 2A over 2. L is A over 2. So that's going to end up canceling. And then we have the square root of L squared, which is A over 2 squared, plus Z squared. Well, Z is the square root of Z squared plus A over 2 squared. So that's going to end up being plus Z squared and then plus A over 2 whole squared again. It's getting a little cramped. So we have, just double check that I'm doing this correctly. I think I am. So we're going to end up having lambda A over 4 pi epsilon naught. And then we have 1 over the square root of Z squared plus A over 2 squared times 1 divided by the square root of, so this is going to be Z squared, and I can combine these two terms with A over 2 squared, so that's A squared over 4 plus A squared over 4, which is A squared over 2. So we have Z squared plus A squared over 2. Okay, so we're getting a little crowded here, but we're getting close to being done. I'm going to try to make this a little bit more clear. So we have the electric field, the magnitude of the electric field due to one of the sides of that square. Let me just reiterate. I have the answers already written out. Okay, so I'm just going to write this out a little bit more, slightly bigger, since I have more room now. So it's going to be the same thing I have up here. I'm just going to write this a little bit more clear. So we have the square root of Z squared plus A over 2 squared, and times 1 over, we have Z squared plus A squared over 2. Okay, so this is the electric field due to one of the sides of the square. Let me grab the original picture. So now we have found the electric field due to one of the sides of the square. However, how do we find, now we have to find the electric field due to the whole square, all 4 sides. Well, you know, like I said earlier, there's no side is special. There's no side that's better than the others. You could rotate this around and the answer would come out the same. So we just multiply by 4 essentially, but not just by 4. We also have to multiply by cosine of theta. And why is that? Well, it's because of symmetry here. This is a perfect square. For every point on this side of the square, you can find an equal point on this side of the square. So if you were to draw out the field lines from every point on the square, and draw the components, what you would find is all the horizontal components, for the same reason essentially that the horizontal components cancel out in this, except this is two-dimensional. This becomes a little bit more of a three-dimensional sort of cancellation, but it's the same principle. All the horizontal components would cancel out here. So this point, right, this, if you can imagine a little piece of charge here, produces a field out this way. And similarly, a little piece of charge over here would produce a field out this way, right? And the horizontal components cancel out. Same with the charges over here, except I can't really draw that because it's going into the page, and this one would be coming out of the page, but the same thing. So really what we care about is the vertical component of the field. That's the only thing that contributes to the electric field in this problem. So we multiply by 4 to account for all sides, all 4 sides, and we multiply by cosine of theta for the same reason that like the vertical component is, you know, the electric field times cosine of theta. So the total field is going to be 4E1 cosine of theta, which is just going to be, so we have 4 lambda A over 4 pi epsilon naught times 1 over the square root of z squared plus a over 2 squared times 1 over the square root of z squared plus a squared over 2, just like we had before, and then times cosine of theta. And in terms of our problem here, cosine of theta is z over script r. So we have times z over script r, which is, in our problem, the square root of z squared plus a over 2 squared, which this term is exactly the same as this term, so those square roots will end up canceling each other out. And so what we find is the total field is 4 lambda A. Here, I'll put, let's see, 1 over 4 pi epsilon naught out front. 4 lambda A over z squared plus a over 2 squared. 4 lambda A z, because the z over here is still there. And then times 1 over this square root term, z squared plus a squared over 2. Let me just double check that that is indeed what I got. All right, so yeah, this is indeed the correct answer. So yeah, that's pretty much it. I hope this wasn't super complicated to follow. I know this argument between making the relationship between the problem we had presented to us and this example problem made sense, and how we sort of went from this to building up a solution for this. And yeah, so if you guys do have questions, feel free to let me know in the comments below. And yeah, I can't wait to see you guys in the next video for problem 2.5. As always, thank you for watching and have a great day.